In this video, we are going to learn how to graph rational equations. Label the quadrants of the graph below. So you'll recall that this is quadrant 1, quadrant 2, quadrant 3, and quadrant 4. Then, use a graphing calculator to sketch the graph of the function f of x equals 1 over x. So I'm going to use Desmos as my graphing calculator. So I am going to go to desmos.com and I am going to click on the graphing calculator. And now I'm just going to type in our function 1 divided by x. And you can see that our function is in quadrant 1 and quadrant 3. Notice how we get really close to that x-asymptote or that x-axis, but we never cross or touch it. Same thing with our y-axis. We get really close to that axis, but we never cross or touch it. And that is because we have horizontal and vertical asymptotes there. So remember that an asymptote is a line the graph continually approaches. The asymptote guides the end behavior of the function. So our vertical asymptote, let me grab my colors. Our vertical asymptote was where x equals 0. And so that is our y-axis. So that's right here, x equals 0. And our horizontal asymptote was y equals 0, and that is our x-axis. So remember, horizontal goes left to right, and vertical goes up or down. And so our graph we said was in quadrants 1 and 3. They are curves. They get really close to those asymptotes, but they do not cross or touch them. You do not want to make these 90-degree angles. They are curved, so they should not be a sharp L there. You should have a curve in those places. So this is what the basic graph of a rational equation looks like. We can transform these graphs just like how you did with linear, quadratic, and exponential functions. So let's go ahead and dig into that with these examples down here. It says graph the following rational equations using a graphing calculator. Again, I am going to choose to use Desmos. You could use whatever graphing calculator you feel the most comfortable with. And we're going to identify any transformations as well as the domain and range. So example 2 is f of x equals 1 over x plus 1. So I'm going to leave my parent function here. And in line 2, I'm going to type in 1 divided by x. I'm going to get out of that fraction and then do plus 1. So our blue graph is the transformed graph here. And we're trying to figure out how we went from the red graph to the blue graph. And it looks like everything is shifted up 1 unit. So here my transformation is up 1 unit. And when we go up 1 unit, that is going to affect our horizontal asymptote. Instead of our horizontal asymptote being at y equals 0, it's now going to be at y equals 1 because it has shifted up 1 unit. If we shift our vertical asymptote up 1 unit, it's still going to be in the same location of x equals 0. Remember, these lines go on forever, so shifting this up 1 doesn't really have an effect on our curve. Our curves were still in quadrants 1 and 3. So again, we are just going to get really close to those asymptotes, but we are not going to cross or touch them. Your domain are your x values from left to right. In these cases, your domain is always going to be related to your vertical asymptote. So my domain is going to be all values of x such that x cannot equal 0. So my domain cannot include my vertical asymptote because we never cross or touch this asymptote. And so I can have all the real numbers except for this line, which is 0. Our horizontal asymptote is y equals 1. So that means that my range is going to be all values of y such that y cannot equal 1. And so that comes directly from our horizontal asymptote. And that is because we can have every single other y value except for this line right here, and this line is when y equals 1. Let's look at the same thing for example 3. Here we have g of x equals 1 over x minus 1. If I open up Desmos here, I'm just going to go ahead and change this to minus 1. And now I can see that everything has been shifted down 1 unit. Oops. So here we're going down 1 unit every time. And so our transformation is down 1 unit. So that's going to, again, have an effect on my horizontal asymptote. So if I shift down 1 unit, then y will be negative 1. Because remember, our parent function is when y equals 0. And so if that asymptote shifts down 1, then it will be at y equals negative 1. Well, that's going to have a direct effect on our range. Our range will be all values of y, such that y cannot equal negative 1 because we have a horizontal asymptote there. When we shift down 1 unit, that has no effect on our vertical asymptote. So our vertical asymptote is still at x equals 0. And so our domain will be all values of x such that x cannot equal 0 because we have a vertical asymptote there. Our curves were in quadrants 1 and 3. And so we will get very close to those asymptotes, but we will not cross or touch them. Let's go ahead and check out example 4. Here we have h of x equals 1 over x minus 1. So now that minus 1 is inside of my denominator. So I'll have x minus 1. And if you look, it looks like everything has been shifted right 1 unit from our red graph of the parent function to our blue graph. So now we have gone right 1 unit. When we go right 1 unit, that has no effect on our horizontal asymptote. Instead, it has an effect on our vertical asymptote. If we shift our vertical asymptote right 1 unit, now instead of x equaling 0, x will now equal 1. So now my vertical asymptote will have been shifted right 1 unit. And so my domain will be all values of x such that x cannot be 1 because we're going to have a vertical asymptote there. If we if we shift our horizontal asymptote right 1 unit, because this horizontal asymptote goes forever in both directions, it's not going to have a major effect on that. And so our horizontal asymptote will still be at y equals 0. And so our range will be all values of y such that y cannot equal 0. Our curves are still in quadrants 1 and 3, and so we get very close to those asymptotes, but we do not cross or touch them. On example 5, we have y equals 1 over x plus 1. And so I'm going to go over here and type in x plus 1. And now I can see that my blue graph, has shifted to the left 1 unit. So everything has been transformed left 1 unit. And so that is going to have an effect on my vertical asymptote. Instead of being at x equals 0, it will now be at x equals negative 1, which means I will have a vertical asymptote at x equals negative 1, and our domain will be all values of x such that x cannot equal negative 1 because of our vertical asymptote there. Our horizontal asymptote will not be affected, and so that will still be at y equals 0. Meaning that our range will be all values of y such that y cannot equal 0 because of that asymptote. And our curves are still in quadrants 1 and 3. We get very close to those asymptotes, but we cannot cross or touch them. Let's look at example 6. With example 6, the major change here is that now our function is negative. So if I open up Desmos, I'm going to have negative 1 divided by x. Oops, I did that in the same line. New line, -1 divided by x. And you can see that we've had a reflection across the x-axis. What this curve is has become this green one here, and what this red curve is has become this green curve here. So we have a reflection across the x-axis. Let's change my color here. And so that has no effect on our asymptotes. My vertical asymptote is still going to be x equals 0. And so my domain will be all values of x such that x cannot be 0. And it doesn't affect my horizontal asymptote, so that will still be y equals 0. So my range will be all values of y such that y cannot be 0. And if you notice, our major change here was what quadrants our graph is in. Our quadrants, or our graph is now in quadrants 2 and 4. So we're going to get very close to those asymptotes, but we will not cross or touch them. On example 7, here we have j of x equals 3 divided by x. So here the major change is that we have changed our numerator to be 3 instead of 1. And what you can see here is that the gap between our asymptotes is larger. So we've stretched that. This is a vertical asymptote of 3. Where did my thing go? Here we go. So this is a vertical stretch by 3. And that has no effect on our asymptotes. So our vertical asymptote is still x equals 0, which means our domain is all values of x such that x cannot be 0. And our horizontal asymptote is still y equals 0, meaning that our range is all values of y such that y cannot be 0. And we're back in quadrants 1 and 3, but now the space in between where our asymptotes are is larger. So this space right here is in between is bigger, between the curve and the asymptotes. So here we have some rules, and you'll notice the A, H, and K. It's the same A, H, and K that you had when we talked about transformations with quadratics, linear functions, and exponential functions. It's the same exact rules as well. So A, that will tell you if you have a stretch, shrink, or reflection. It will stretch if the absolute value of A is greater than 1. It will shrink if the absolute value of A is between 0 and 1. And it will shrink, and it will be a reflection if you have a negative number. So if A is negative, it will be a reflection. You can have a reflection and a stretch. You can also have a reflection and a shrink. In your denominator, you'll have x minus h. If it's x minus h, then that means that you've translated to the right h units. And if you have x plus h down here, then that means that you will have gone to the left h units. And then your k on the end will tell you if it's greater than 0. So if it's a positive, you will go up k units. And if k is negative, then you will go down k units. So on example 8, it says using the knowledge of the parent function f of x equals 1 over x and its transformations, sketch the graphs of the following equations without a graphing calculator, identify the transformations, asymptotes, domain, and range. So let's take these one at a time. For example 8, the first thing that I notice is my a value is 4. That means that I have a vertical stretch of 4. Which also tells me that I'm going to have a larger gap from my asymptotes. The next thing that I notice is that I have x minus 2. Well, minus 2 means that I'm going to go to the right 2 units. And that will have an effect on my vertical asymptote. If we shift to the right 2 units, then my vertical asymptote will be at x equals 2, which means my domain will be all values of x such that x cannot equal 2. And then the last thing that I notice is that my k value is positive 3, which means I'm going up 3 units. Well, if we go up 3 units, that means that my horizontal asymptote will be at y equals 3. And my range will be all values of y such that y cannot equal 3. We didn't have any reflections, so our curve will be in 1 and 3. And remember to leave a gap between your asymptotes and your curve because we did have a vertical stretch. So that is what example 8 looks like. We did all of that without using a graphing calculator. Let's try that again with example 9. On example 9, the first thing that I notice is that my A value is negative. That tells me that I have a reflection across the x-axis. That means that my curve is now going to be in quadrants 2 and 4. The next thing that I notice is that my A value is 2, so that tells me that I'm going to have a vertical stretch by 2, which tells me that I'm going to have a gap in between my curve and my asymptote. Then I see that I have x plus 3 in my denominator, which tells me that I'm going to the left 3 units. If I go left 3 units, that is going to have an effect on my vertical asymptote. That means that my vertical asymptote is going to be at x equals negative 3. And so my domain will be all values of x such that x cannot equal negative 3. And then the last thing that I notice is that my k value is negative 1, which tells me I am going down 1 unit. Well, if I go down 1 unit, then that means that my horizontal asymptote has shifted down to y equals negative 1, and that my range will be all values of y, such that y cannot be negative 1. Because of our reflection, we are going to be in quadrants 2 and 4. And then because of the stretch, I'm going to leave a little bit of a gap. So here, this is what this curve would look like. So there you have it. Those are the basics of graphing rational equations.